This video is about conditional statements. If P then Q is a conditional statement, it means that if we have P, then we also must have Q. P is the condition for Q. We use the arrow to show this. We call it a conditional statement. We also call it an implication. We read it as if P then Q, referring to our arrow here. We would also read it as P implies Q. Two ways to read it. P is the hypothesis. That's the beginning statement, also known as the premise or antecedent. Q is the conclusion, also known as the consequence. Here's an example. If we get a storm, school will close. There's an understood then right here. You don't always see it when it's written in English. Our hypothesis is we get a storm, and the conclusion is school closes. Now, when is this implication true? It turns out it's actually easier to decide when it's false. Let's think about what circumstances would make it false. The statement is, if we get a storm, school will close. If that was a lie, let's say somebody told you that, and you said, no, that is a lie, what would have to happen to prove that it was false? We would have to get a storm, and school doesn't close. That would make the statement false. That's really the only event that actually proves the conditional statement false. If we don't get the storm, we can't really say that the statement is false. And we're going to accept it as true until proven guilty. So the statement is true in these cases. If we get a storm and school does close, that's kind of just what we're looking at in that statement. If we don't get the storm, we're going to accept the statement, the implication is true. Whether school does close or school doesn't close, if we don't get the storm, we're going to accept our statement as true. Here's our definition. The implication is a statement that is false when P is true and Q is false. And otherwise it's true. Of course, we could use a truth table to define it. Keep in mind we said it's false when P is true and Q is false. So that really is this case right here. This says that, well, P happened and then Q didn't happen. So if P then Q was false. All the other cases are true. So notice if the hypothesis is false, that's these two cases, then the implication is true. Because in our previous example, we said if we don't get the storm, we can't really call the statement false. Remember, if the hypothesis never happens, we accept it as true. Secondly, true implies false is the only way that the implication is a false statement. Here's our original. We'll use the same example. Decide whether it's true or false under each circumstance. Pause the video, make your decision. First case, we don't get a storm and school does close. What is the original, true or false? In this case, the hypothesis did not happen. Remember, P was we get a storm. We didn't get the storm, so it's automatically true. If our hypothesis didn't happen, we accept implication as true. Suppose we don't get a storm, same reasoning, it's automatically true. Whether school does close or doesn't close, if we didn't get the storm, we consider the implication true. Now if we do get the storm, so now the hypothesis does happen, school does close, our hypothesis happened and the conclusion happened. So this is our case for true. This is sort of what we're expecting. There was a big storm and school did close. Here we get the storm, school does not close. That means our conclusion did not happen even though the premise happened. So this is our case which is false. For P implies Q to be true, either our hypothesis is false, which happened in our first two cases. This is where the hypothesis was false and we ended up with a true statement. Or if the hypothesis isn't false, putting us in the next two, so in other words, if we do get the storm, then Q must happen. Q must happen. And so either P is false, that's where the hypothesis didn't happen, we didn't get the storm, or the conclusion must be true. Now we're going to rewrite that to say if P is false, then that means that not P is true. And here we have Q is true, so look what we have. P implies Q is logically equivalent to not P or Q. With order of operations, implication is done last. So if you have a compound statement like this, you would do each of the pieces first, and then after that you would evaluate the implication. Converse, inverse, and contrapositive. These are new statements that we can create from the implication. Our original is P implies Q, Q implies P is the converse. Not P implies not Q is the inverse. We keep the same order, but we negate the premise and we negate the conclusion. That is the inverse of the original. Now we're going to take the inverse and swap those out to get the contrapositive. Here we negate the premise, we negate the conclusion, and we also switch them. That's how we get the contrapositive. One of these is equivalent to the original. In other words, it has the same truth value as the original. Do you know which one it is? Let's use an example. Here's a new example. If I attend college, then I am a student. Seems like a true statement. But whether it's true or not, we can create the converse, inverse, and contrapositive. Think about what the converse is. You might jot it down and then pause for a moment. Continue this video once you have it written down. If I'm a student, then I attend college. Let's try the inverse. Again, jot it down and then continue. The inverse is, if I do not attend college, then I am not a student. Notice we keep the same order, but we negate each one. For the contrapositive, we have to negate each one and switch the order. Think about what that comes out to be. If I'm not a student, then I don't attend college. Let's think about which one is the same as the original. If we take the original to be true, seems like a reasonable thing to do. If I attend college, then I am a student. So, if I am a student, do I have to attend college? Not really. I could be a high school student. If I don't attend college, does that mean I'm not a student? Once again, maybe I don't attend college, but I'm a student at another kind of a school. Let's look at the contrapositive. If I am not a student, I don't attend college. In other words, if the conclusion doesn't happen, then the premise didn't happen. That is the one equivalent to the original statement. I just did it by thinking about it, but we can prove it with a truth table. Now here's some alternate phrases. P if Q, well, that's the same as if Q then P. P only if Q, well, that means that P is going to happen only if Q happens. That actually means if P then Q. If P happens, Q has to happen. So that's P only if Q. We can combine these to P if and only if Q, and that's really the two statements above combined together with and. So that's if P then Q and if Q then P, and now we have this new symbol, and that is called the biconditional. The fact that it's equivalent to P implies Q and Q implies P, that's not actually the definition, but that's something that we could prove. Let's get the actual definition. Here's our biconditional. This statement is going to be true if P and Q have the same truth values, and otherwise it's false. And IFF is used as an abbreviation. It means if and only if. Besides the definition written above, we can use the truth table to define P if and only if Q. This biconditional is true when P and Q both have the same truth values. So if they're both true, the biconditional is true. If they're both false, the biconditional is true. Those are the two cases where it's true, and in the other case, if either one is false, then this biconditional is false. That's how we define P if and only if Q. Now let's talk about order of operations. We have our negation, which is first, the and or are second, and then last are the conditionals, which would be either the simple conditional or the biconditional. Two more phrases here. A is a sufficient condition for B. Let's think about that, what that means. A is enough, it's sufficient, or it's enough to say we have to have B. That's going to be A implies B. A is enough to say we have to have B. Now the second one says A is a necessary condition for B. A is necessary for B. So that means if we have B, then we must have A. That's actually B implies A. A is necessary for B, which means that if we have B, we will have A. It's a little tricky. It takes a little thinking about. We actually define these. R is a sufficient condition for S means R implies S, and R is a necessary condition for S means S implies R. You could also think of that as not having R means you don't have S. Since R is necessary for S, if you don't have R, you don't have S. This one might make more sense when you think about it, and these two implications are equivalent to each other, so either one could be the definition. Here's a table of a number of phrases. All of these are equivalent to if P then Q, or P implies Q. All of these are equivalent to P implies Q, and all of these are equivalent to the biconditional P if and only if Q. So some may be very clear to you, if some are not. Take a look at them a little later after you've practiced these conditional statements. And that is the end of our video.